Okay. That's about the best I can do with what we got now. Okay. Let's get PowerPoint started from the current slide. We'll be ready to go. Now, we did this last time. Now it's cut back. Now, why, I'm not sure, but it did. I guess it's, I don't know, but it's okay. We talked about the cross product, gave that definition last time. We're ready for example 2, and this is the best place I could think to do it. Calculate this. V, oops, let me get my pen. Okay. V cross W, where, goodness gracious, this is a pain in the neck. V is equal to the vector negative 2, 1, 4, and W is the vector 3, 2, 5. Okay. Now, you can do it this way, but really the better way to do it would be, wait, I'm sorry. Yeah, no, yeah, this is the better way. I'm sorry, I was looking at the wrong thing on this slide. So, as I suggest here, how you set up V cross W would be to set up a determinant with the top row being the unit vectors I, J, and K, and then the second row, the first vector across here. Let me say this. Remember on dot products were commutative. Didn't matter. Cross products, not commutative. Only very rarely will you find one that is commutative. In fact, what usually happens if you commute, if you think about right-hand rule, if this is V and that's W, then the product is going to be in this direction. Okay? If you do V cross W, your product is going to be in that direction. So it's going to be the opposite. So usually, I mean, just about always, order matters with cross products. So put the V second, that's negative 2, 1, 4, and then W, 3, 2, and 5. Now, the book does one way. I think y'all said Dr. Bryant, and I prefer this way. Copy over the first two columns. Okay? I minus 2, 3, J, 1, 2. Okay? And now I'll do it this way. From the I, go down to the lower right. 5 times 1 is 5. And then find your other I and go in the opposite direction. What do you get? Minus 8. Okay, anytime you're sloping downhill from left to right, it's a positive. Uphill from left to right, or downhill right to left, that's a negative. So this will be a minus 3I. Okay, do the same thing with the J's. What I'm going to do now is wipe out these so you don't get them confused with the J's. Okay, downhill from the J to the right is, that would be a 12. And from the other J going in the opposite direction, what do you have? Minus a negative 10, is that what you said? Yeah. Which is plus 10. So that would be, well, we'll get to that. That's your J component. And now erase those so you can see better. Okay. And get my pen back. All right. And then the K component, you got it right there. What you got? Negative 4 minus 3. And what do you have? That's the K. And by the way, you don't have to do the I and J. The I, you do this square, J, you do that square, and K, you do that square. So you don't have to go backwards from it. That's the other way to look at it. But anyway. And this takes care of your signs and everything. So what do we have? Negative 3I plus 22J minus 7K. The cross product of those two, really a weird setup. Ooh, they have a minus 22. Did I do something wrong there? Oh, wait. No, they do a minus, making it plus. Got it. Okay. And then writing this in angle bracket notation, this would be angle bracket negative 3, 22, negative 7, which is a little short, more of a shorthand, less writing, so lazy people tend to like it. Don't you, Cameron? Okay. So, any questions on how to do cross products? Now, I did, picking your weird way of, You did the weird way of doing it. That's one weird way, but the other is wipe out the top row in this, and then do the cross product here. For J, wipe out the cross product of the top in here, and do this block here, and then wipe out the cross and this, and do that block there. It's always the block to the lower left or lower right.
So for, let's say J.
J, yeah.
That'd be negative 2.
Okay, J, you wipe out this and this, yeah. You do.
I was doing, like, not that way, the normal way.
Okay. Yeah, if you do it the other way, this way here, then this is a minus J, and that would be...
Okay, that's what I was leaving off, the minus J part.
Yeah. Oh, I see. And you're going to multiply by 5. Okay. Good. So that's another way to do it. Both ways work. All right. That's example 2. Now, it says here, Formula 3 gives no hint of the geometric meaning of the cross product. However, and I already gave this hint, when you're crossing two vectors, the resultant vector is in neither direction of the first two vectors. Dot products, you can think, well, that makes a scalar, but you can picture that. But a cross product, whatever the two vectors are, with one exception, if you have parallel vectors or vectors in the same direction, cross product is 0. Okay. Even anti-parallel, anything that would be like that. But if they're crossing anywhere, okay, they cross anywhere, the cross product of those two, whatever plane those two vectors are in, the cross product is always perpendicular to both of those vectors, to both of them. So it's not even in the same line with either of them. Okay. So, if the direction, okay, yeah, I think we've already done that. So let's move on. Oh, here's the right-hand rule. So, blow it up. Okay. V and W. As long as they're not along the same line, okay? As long as there are any two vectors that intersect at one and only one point, V and W, when you do the cross product, the resultant U is going to be perpendicular to V and perpendicular to W. Perpendicular to both of those. Now, these two don't have to be perpendicular to each other, not by any means, but this one will be perpendicular to each of those. You've got 3 dimensions you can play with, make that happen. And that's what we call a right-handed system. Prejudiced against us lefties. Okay, so here is our theorem 1. Oops, I can do it this way. Just extra clicks. All right. The geometric description of the cross product. Cross product of V cross W is the unique vector. Number one, the cross product is always a vector. Dot products, always scalars. Cross products, vectors. Two different ways of multiplying vectors. One produces a scalar, one's a vector. So the cross product is a unique vector, one and only one vector, with the following three properties. The cross product of V and W is orthogonal to V and orthogonal to W. Okay? V cross W, and here's a new one. V cross W has a magnitude or length, magnitude of V times magnitude of W times the sine of theta. That looks pretty familiar, doesn't it? What does that look like? Very similar to the dot product of two vectors, except that's the cosine here. And for a dot product, that is the dot product. This is the length of the vector. This isn't the dot product, this is the length of that vector. Okay? Where theta is the angle between V and W. And it always has to be acute. Don't have V in this direction and W in that direction. Do it the other way. Okay. Is there?
Reflection off his watch.
Oh, I see.
Saw
Okay.
something going across the room. I was like,
Yeah. Okay. Now, and number three, the set of V, W, and the cross of V and W forms a right-handed system. And we basically, not quite said that, but came close to being the same thing as this. Okay. Now, getting here, theta is the angle between V and W. Oh, I said acute angle. It must be, it's always between 0 and pi. And you, so you could have V in this direction, W in that direction. Yeah, that's between 0 and pi. So yeah, you're fine there. That's really not an issue at all. Mostly because it's a sine. If that was cosine, it would make more of a difference. Okay. I think we're ready for example 3. Let's see. No, this is the verbiage, I think, after that theorem. What's that?
the more right-hand rules.
Yes. How do these three properties in that first theorem determine V cross W? Property 1 basically identifies the line that it's along, okay? And basically sort of tells you the direction too, but not quite. Property 2 gives you the length of that vector, and property 3 tells you which of the two vectors is right-handed. It points in the right direction. So the first property gives you the line. The second property gives you the magnitude, and the third property gives you the direction. Okay. Which, to me, the first and third are awfully closely related. All right, I think we're now ready for example 3. Let's see if that's what this is. Oh, no. Nope, anyway. Yeah, this is it. Let V be the vector 2, 0, 0. That's our V right here. W be the vector 0, 1, 1. No. Yeah. W. There, no?
Kind of an odd graphic, isn't it? Just bring the thing over it like that.
Yeah.
It's like a group graphic.
Yeah, that's slide 4. I mean, the next slide on top of this one, which is rather bizarre. Let me.
Zoom out.
What's that?
Zoom out.
Let's go back one
There you go.
and back another. No, going forward. Nope. Can't get rid of it.
That is just strange.
It really
There
is.
it goes.
I know, that gets rid of the hand, but I can't get rid of this. This is going to be there no matter what. Okay? So, you don't see vector W here. You see part of its components sneaking out there. Yeah, in fact, you see the whole components. But it is a vector somewhere up this way, okay? It's just buried in the picture here. It's 0 on X, 1 on Y, and 1 on Z, so it's basically up in a somewhat direction like that.
Somewhere around the tip of
That's W. Now, and it is, you know, you think about it, it's got to be a little bit shorter than V is. That has a magnitude of 2. This one has a magnitude of 0.11, square root of 2. Okay, 1.4. Okay. This is hard to see in this light. Jonathan, right? Okay. My last projector blew a bulb, so we have this one a little bit smaller display here. In order to get it bigger, I've cranked it up as far as the zoom will go, but I'd have to be about halfway back in the room to do it, and that just was awkward. That's too far from the plug. People would be tripping, so did this. Okay. You came in on a really lousy slide because we got 2 slides on top of each other. You can't see the vector W back here. Okay, but this is example 3 on page 655 in section 12.4. Okay, it says determine the vector U that they're showing here, which is V cross W, using the geometric properties of the cross product rather than equation 3, which we used before. Okay, so first, goodness, good deal. They keep them coming. Okay, here's Tony. So just missing Ashley, Victor, and Giovanni. Okay, but again, all Y chromosomes on the story of my life. Okay, so we need to find this vector using the geometric properties rather than the cross product. Okay, first, along what line is this vector? V cross W. With along the line that's perpendicular to V, but also perpendicular to W. But you can't see W behind there somewhere. Okay? So that gives you the line, and that's that dotted line that you see there. It's somewhere along that dotted line, perpendicular to V, perpendicular to W, but you can't see. Number 2, what's the magnitude of the vector? The magnitude of the vector, U, now of course to right now it's going to shrink. Okay? The magnitude of U, which is the cross product, is equal, okay, they do a double line for magnitude. Magnitude of V times the magnitude of W times the sine of the angle theta in between the 2 vectors. Okay? So how do we determine that? Magnitude of V, that's pretty easy. What is that? Which is 2. Okay? It's going 2 in the x direction, 0, y, 0, z. It's 2. It's 2. The magnitude's 2. Okay. W, 0, 1, 1, that would be the square root of 0 squared plus 1 squared plus 1 squared, square root of 2. So this will be the square root of 2. Now, the sine of the angle in between. How do we get the angle in between? they said don't use the cross product definition, which actually tells you how to calculate it. So we can't use that, they say. How would we get the angle in between? Well, they didn't say we couldn't use the dot product, okay? And how is the angle related to dot product? Can you remember that one? Cosine of theta is V dot omega over magnitude V times magnitude W, right? All right, and then take the inverse cosine of that. So we can do V dot omega W, and what is that? Dot product of this one and that one. Here the order doesn't matter, but who cares? What you get is a dot product. 0. What does that tell you? If the dot product is 0, what does that mean? They are orthogonal to each other. So the angle is 90 degrees. Well, what's the sine of 90 degrees? 1, okay? So we didn't need anything else, so this is just 1. So the magnitude is 2 root 2. Okay? So we got the length of that vector. And then finally, which direction? Well, V is in this direction, W is in that direction. Right-hand rule hasn't been pointing up the way they're showing there. So we have, and we know it's perpendicular to each of those. So we basically have, does that give you coordinates? Not really, okay? You can get coordinates using the other method, but this just, what it says here is determine that using the geometric properties, okay? All right. We also, let's see, this is somewhat, says U points in the positive Z direction, at least somewhat, and the Z component is positive is what they mean by that, okay, just by looking at that. Now, you have to have a vector that's perpendicular to V, perpendicular to W, and pointing upward in Z, positive Z. So, we already know those two are perpendicular to each other. We need to get a vector that's perpendicular to this one and to that one. Okay? Now, looks like a job for dot product again, doesn't it? Let's name this vector U, U1, U2, U3. Okay? And from this we know that 2U1 is equal to 0 because vector V dotted with vector U has to be perpendicular. So what? Guess what? U1, whoops, y'all let me do that, didn't you? That was totally wrong. You don't put vector symbols over the coordinates, okay, just over the vectors. So U1 is equal to 0. I don't know what that is there. Yeah. Okay. So U1 must be the first component has to be 0. Okay? We also know that the dot product between these two vectors is 0. Well, U1 times 0 is 0. We know that. So that says that U2 plus U3 is equal to 0. No, I'm sorry. Wait. Goodness gracious. All right. That may have been right, but okay. The dot product between these two is 0. Yeah, that was right. U2 plus U3 is equal to 0. Okay? Now, basically that tells you that U3 is equal to the opposite of U2. Right? Now, or maybe I should have said it the other way. U2 is opposite of U3. It really doesn't matter. They're both true. What the third thing tells you is that the z component is positive. So this says the y component has to be negative. Same value, but negative. Okay? Now, we also know that the magnitude is that. So that tells us that the square root of u1 squared plus u2 squared plus u3 squared is equal to that, right? But what is u1? Zero. Okay, this is 0. So we know that the square root of u2 squared plus u3 squared is equal to 2 root 2. Now I'm going to square both sides of that. Okay? What does that give me? u2 squared plus u3 squared. 8, exactly. 2 squared is 4 times 2, 8. Okay? And we know these two have the same magnitude. Okay? So basically, whichever one you choose, this is going to be the same as saying u2 u3 squared is equal to 8. If plugging u2 is equal to negative u3, and it's negative u3 squared would be u3 squared, plus u3 squared would be 2u3 squared is 8, right?
As you square out the negative goes away.
Second? Yeah. Okay. Divide by 2. Not bad. And you get 4. So u3 must be, it could be plus or minus 2, but we know it has to be going upward, so that would be plus 2.
That means u2 is minus 2.
And that makes u2. So here we found what the u vector is 0, minus 2, 2. Now, I'm not sure that's the same way the book did it, but it's okay. Yeah. 0, negative 2, 2. Now, one of the most striking properties of the cross product, I don't find it all that striking, but the book does, is that it's anti-commutative, and that's what the block that was covering our v vector, our w vector, was showing, is this. And this is what I've already described to you before. If you do u cross v, it's this way, v cross u, it's exactly the opposite direction. Same magnitude, opposite direction. They call that anti-commutative. Why they changed? Well, yeah, this is fine. W cross V is the opposite of V cross W. It's the same magnitude, same everything, except opposite direction. That's why it's not commutative. It's exactly anti-commutative, meaning it's exactly opposite. Same value, same magnitude, but opposite direction. Okay. And I said that when we were setting up the determinant to do. I say you have to have it in this order because I did the picture. But if you actually put them in reverse order, you'll see you're going to get exactly opposite everything, because your signs will be exactly reversed on every component. Okay. So that then leads to, I guess this is a picture of the anti-commutativity. Okay. This is V cross W is V cross W up like this. But if you did W, you have to use right hand still. W cross V, it points exactly in the opposite direction. Exactly the anti-commutative. It has to be because this forms a plane, and the cross product has to be perpendicular to that plane, so the only other option would be this way or that way, and they have to be exactly opposite each other, and of course the magnitude is the same because the magnitude of U, the magnitude of W, sign is the same as the angle in between, so you've got to have that. No way around it. Okay. That leads, I think, then, to Theorem 2. All right, and this is kind of a summary of some of the things we've already talked about. At the same time, let's see, is there anything new here? Probably a little bit new. Okay. Basic properties of the cross product. Number one, primary everything. The one they say is really striking is the anti-commutativity. That the cross product is not commutative, but it's not randomly not commutative. It's exactly anti-commutative. The other one I told you already was V cross itself is 0. Any vector parallel to a given vector, the cross product is going to be. And remember, this is not the number 0. This is the 0 vector. Okay? If this is a three-dimensional vector, that's a 3. This is a 0, 0, 0, a three-dimensional vector there too. And then an extension of that, if V cross W is 0, that's true if and only if these two are, that W is some multiple of V. Okay? In other words, V could be here if W is a large multiple of it, same direction but just longer, or smaller, same direction but shorter, negative, same line but opposite direction, either longer or shorter. So W and V are collinear for some scalar lambda. Or the only other possibility then would be if V was the 0 vector, which, or you could say W is the 0 vector. I don't know why they say pick just V. So either one of these two is a 0 vector, or these are collinear with each other. That, to me, would be the better way of saying it. All right, then number 4. If you multiply a scalar by a given vector, cross it with W, that's the same as V crossed with that same scalar times W, which both of these produce the scalar times the cross product. But the order of the cross product must be the same, but you can pull the scalar out. You can pull it out here, pull it out here, pull it out here. It doesn't matter. It's the same. So this scalar just crosses 1. Now that's just one scalar. Okay. Now, so that's sort of a, if you look at it this way, a distributive law of a scalar over a cross product. And this is undoing that. Okay? The fifth of these is another sort of distributive law that the sum of two vectors crossed with a vector, W, is going to be the first cross W plus the second cross W. In other words, you can vector addition distributes over cross product multiplication. Okay? Or you can have vector U cross with the vector addition of V and W. It just changed the order here. That means U cross V plus U cross W. Okay? But you can't reverse these two. That's going to give you anti-commutativity then. So you can't. So you have to keep the order right when you do those. Okay. Any questions on those basic properties? They should be a little bit expected. I'll put it that way. Okay. Now let's look at some other ramifications of those. Let's look at some of our favorite unit vectors, our component, what would you call that? Coordinate unit vectors maybe is the best name for it. Okay? If you cross the I vector, which is in the positive x direction, with the j vector, which is in the positive y direction, you're going to get the k vector, which is in the positive z direction. So I cross j is equal to k. And as long as you keep the same order with it, j cross k is equal to I, and k cross I is equal to j. As long as you keep that ijk, as long as you keep the order that way, it works. Also, if you cross I with itself, or j with itself, or k with itself, of course, those are parallel vectors, so they are going to be the zero vector. Remember, cross product produces a vector. Now, what they didn't say here, but you could just as easily have said, what happens if you cross j cross I? Negative k, and k cross j, negative I, and I cross k, negative j. So you have exactly the opposite. Okay, very good. That's the anti-commutativity property brought into play. All right, I think we're ready with, for example, 4. And I don't think there's a figure with it. But before we do that, I guess they're showing this figure. So this goes with the last one. Okay. If you think of it this way, I, j, and k, and make them clockwise. Then whatever, as long as you're going clockwise and doing the cross product, I cross j is k, j cross k is I, k cross I is j. As long as you're going clockwise, you'll have positive values, the positive of the next vector. But if you go counterclockwise, it's going to be negative. I cross k is negative j, k cross j is negative I, and j cross I is negative. They didn't show that, but that also works to that way. All right, now I think we're ready for example 4, but it doesn't have a figure, so we'll use this one. Not use it, but just use the slide, because it's easier than pulling up the other. What's that?
Widening the screen.
Widening the screen?
Widening the screen.
Oh, yeah. But the other thing is, now that you got that presenter view off, it's easier than it was. Because before, every time you went out and came back in, you had to get out of presenter view and all that kind of stuff. Okay. So example 4. Compute this. 2i plus k crossed 3j plus 5k. Okay. is your attack on that?
So it's just kind of like distributed property, right? Or, well, kind of like foiling, I guess.
Yeah, kinda. You have to be careful with this, but goodness gracious, why not go back to the first thing we did, okay? Why not just do it this way? I know that's not what they're intending, but why not? This is my way. This is 2, 0, 1, 0, 3, 5. So this will be a 2, 0 and a 0, 3. Okay? I will be.
I see where you get the 2 and the 0, where the 1 come from. Out of that first group.
Okay. On the first, it's 2i, 0j,
Oh, okay.
and 1k. Okay? So what does that give you? Second?
20.
I can't hear.
20.
20. That's a 0 times 5 is 0. This is a minus 3. So minus 3i.
Minus 10j.
Okay. Yeah, minus 10j
Plus 6k.
plus 6k.
I don't know, doing it the regular matrix way makes more sense to me.
Okay, yeah, you can. There's nothing wrong with this.
I kind of see what you did though, because you go in order.
Right.
That's extra writing.
It is extra writing, and he's super lazy, so okay, we got it. All right, now, let's see if there's any way we can get this off of what we were doing before, as you were suggesting FOIL. Okay? This would be a 2i cross 3j. That gives you our 6k, so that's looking good. 2i cross that's going the other way. That would be a minus 10j, so that's looking okay.
K times 3, or cross
This would be negative 3i because k cross j, that's going counterclockwise, so that would be minus 3i, and then this k cross k is 0. So, sure enough, you could FOIL it as long as you're careful about your direction of travel. Okay? And that would be easier than this.
I think matrix makes more sense though. There,
Yeah,
it's easier,
it does.
You don't have to remember.
Exactly. Yeah. And like I say, he's really lazy. Not wanting to remember anything. Okay, good. Good deal. Okay. You win the prize. Okay. All right. Good deal. So there are a couple of ways to do that. But frankly, I'm more confident in this way, and then I go back to, oh yeah, that makes sense that way too. Okay. But as long as you have a 2 by 2, then the cross is pretty easy. But you know, really, a 3 by 3 wouldn't have been bad either. It's just you have more zeros in there. Okay, this one happened to only have 1. All right, now I think we're ready for example 5. Let's blow it up to begin with. And then we will build from that. Velocity in a magnetic field. The force F, capital F, that is shown, I think, by this blue arrow down here. Okay, I believe that's what they intended the force vector to be. On a proton moving at a velocity of v meters per second, v, remember, is a vector, velocity is a vector too, and they're showing this, it looks like it's pretty close to perpendicular to that force. Well, of course it is. We'll get that in a minute. It's got to be, now that I read the problem. V in a uniform magnetic field, and magnetic fields are vector fields as well, and this is B. Your B tends, at least appears here, to be positive Z direction. Okay? The V looks like it's somewhere maybe in the negative Y direction, maybe a little bit of component in the B direction. I don't know. I can't tell in a two-dimensional graph, but I think it probably looks like it is a little bit. Well, what's the force from that? Well, whose law is it? Not Ampere's law. Whichever law that is in physics, V cross B gives you direction of the force. And sure enough, that's pointing in the right direction. Do they give it here? And by the way, magnetic field B is measured in the SI unit for magnetic field is Tesla, named after Nikola Tesla, who was the Tesla, he is studied under Edison, but disagreed with Edison, and then they broke off pretty bitterly, and he was a proponent of alternating currents, and Edison was convinced that direct currents were the way to go. Tesla actually upped him on that one. I think Tesla teamed up with Westinghouse, who was also a proponent of alternating current, and they won the day, basically. But anyway, the force is Q, which is a scalar quantity. That's your magnitude, the charge on the proton, times V cross B. It's always velocity cross field. And that's what pushes the F to be in the negative X direction here. Okay, and that force is in newtons. Okay, Q is 1.6 times 10 to the minus 19 coulombs. That's the fundamental charge. Positive because it's a proton. And coulombs are capital C. Okay, that's the symbol for it. Calculate F if B is 0.0004 in the K direction. And we said it was in the K direction and positive, so this fits the bill. It's just a very small magnitude. Okay, Tesla's, we would have said Tesla. And V has a magnitude of 10 to the 6th meters per second in the direction of minus J plus K. I thought it looked like it had a little bit of a K component. So minus J going in the back direction here, plus K in the up direction there. Now, according to my perspective, which is never good on this kind of stuff, that looks like it has a much larger Y component than you have the Z component. So it's a little like it's drawn poorly, but who am I to argue? Okay. So let me get that down. The force in newtons. Yuck. Pen keeps grabbing these pieces of paper. Okay. Force in newtons is equal to Q, a scalar quantity, and we know that value, V cross B. Okay. And this is 1.6 times 10 to the minus 19 coulombs. That's your Q. And your V cross B seems like pretty weird numbers here. The V they gave us as minus J plus K crossed with, I probably should put the symbol in there. Cross that with the 0.0004K. Okay. Okay. Probably. Now, notice here, just to keep it from getting confused, when you use IJK notation, you don't need the angle brackets. Only if you're doing pure components without the unit vectors would you put the components of that. So you could have done this as angle bracket 0, -1, comma, -1, comma, 1. Cross that with 0, comma, 0, comma, 0, 0, 0, 0.0004. Angle bracket. Okay. So let's multiply that. Kind of like we did before, J cross K, that's going clockwise around the circle, so that's going to be positive, except you got a -1 and positive that, so that's going to be a minus 0.0004 what? J cross I. J cross K, I'm sorry. I was given the answer. I. And then what happens if you cross your K and your K? 0. Okay. So there is your force. And then you multiply that by the 1.6 times 10 to the minus 19 coulombs. And you get an incredibly tiny number. Okay. It looks like about 6.4 times 10 to the minus 23 newtons. Pretty small. Okay. The force is, oops, I left off my unit, I. And I left off my sign too. Which is exactly what we're seeing here. The force is in the negative x direction. What reminded me I needed my sign in there. And it's an incredibly small force. But then remember, this is a tiny little object, okay? It's a proton. And so basically what that does for you, it gives you in the xy plane basically circular motion, uniform circular motion. And in the but because there is a component in velocity in the z direction, then it's doing this kind of number on its way out. Okay, that if you projected that downward on the xy plane, that would be pretty sure uniform circular motion, pretty close to it. But the just trying to think there's anything special about the rest of it. Okay. Yes. Okay. Okay. Interesting. You did 1.6 times 10 to the minus 19 times 0.0004. All right. What's that?
I didn't do minus 19. Okay.
Okay. Got it. Okay. Okay. I hadn't checked their answer, but I think it should be somewhere in that. Now, wait a minute. You know, They got a different answer, and I'm trying to reconcile that now. Okay, let me think. What have they done here? Oh, wait. Okay. Sorry, I'm misseeing something. It said V has a magnitude of 10 to the 6 meters per second. I missed that one. I just put okay. Where did I get the minus I plus K? I know it was in here, but I don't see it now. There, minus J plus K. Okay, I didn't read the first part. All I saw was in the direction of that, but the magnitude is 10 to the 6th. So we have another 10 to the 6th multiplied by this. So that would give us minus, we still got something to deal with. That would be 10 to the minus 17th. So that's right. The I is right. The Newton's right. But when they say the magnitude of 10 to the 6th in the direction of this, now that's where our problem came from. I was just reading, that was the vector, okay? So what we have to do with that, and this is rather bizarre, to get the magnitude and then the direction separate from that, what you have to do is backtrack and see what those actual vectors would be. Okay? And the way they do it is okay. The vector minus j plus k has a length of square root of 2. We know that. And since v has a magnitude of 10 to the 6th, then v would be, and here's how they do it. V is equal to 10 to the 6th times minus j plus k over the square root of 2. That's divided by its magnitude. This basically gives you the unit vector, because you take the magnitude of the sum divided by that, that's the unit vector. That's the length of that unit vector. So that's where that came from. So you take the answer I had, minus 6.4 times 10 to the minus 23rd, and divide that by, multiply it by, multiply it by 10 to the 6th, and then divide by square root of 2. And if you do that, then you'll get the answer I think they do, 4.5, a negative 4.5 times 10 to the minus 17 in the I, or the negative I direction. Okay, sorry, I'm misseeing that 10 to the 6th. I just thought they had a magnitude, a velocity of that. Okay, wrong. Okay, now let's move on to cross products, areas, and volume. And these are sort of interesting but Some of them are pretty practical, but some of them are just sort of interesting. Cross products and determinants are closely related to area and volume. Consider the parallelogram P. I guess this is the parallelogram they're talking about here. Okay. The magnitude of V cross W, this, is magnitude of V times the magnitude of W times the sine of the angle in between. Well, the magnitude of V is the length of V. Magnitude of W is the length of W. The sine of the angle in between would be the ratio of the opposite, which is this perpendicular distance, to the hypotenuse, which is W again. And if you think about that, the magnitude of W times the sine of this angle is that height here. And the height here times the V here, just move this up there, you're going to get the area of that parallelogram. So yeah, that is the area of that parallelogram. Now, how many times this week have you said parallelepiped? Okay, probably not a word you use a lot, but it sure has a pretty sound to it, parallelepiped. You know, it's got lots of P's and L's in it. But that is a box someone sat on, okay, basically, and it sort of distorted it a little bit, spin it a little bit. And that parallelepiped, which is V cross W, that's in there, but then you dot the vector U with that. That is, and then the magnet, and the absolute value of that. This isn't magnitude, the absolute value of that. Because this could come up with a negative number. Take the absolute value of it. That would be the volume of this parallelepiped. Okay. They don't do much beyond showing this. But notice this. This U is not the cross product here. The cross product here is shown here. This U is part of the parallelepiped. It's not part of V cross W. Okay, V cross W just happens to be that red arrow that way. Okay. Trying to see where this is in the text. This is at the bottom of page 587. Before you get there, here is no, sorry about that. Back up, back up. With this picture goes the areas. They just don't show it, so I think I'll write it in here. The area of this parallel, well, they actually show it here. The area of this parallelogram is V cross W, okay? And where in the world is, oh, here it is. We know that the area of a triangle spanned by a non-zero, now that's one they didn't show here. Sorry about that. If you take this and draw a diagonal across there, you exactly take half of that parallelogram, okay? Exactly half of it, okay? So the area of this triangle, we'll call that T, they write it sort of funny, is equal to V cross W. I think they double bracket it. divided by 2, which is exactly half of the other. That is not on the slides, but it is in your book. Okay. Then they do the parallelepiped, and then they do, this is what's at the bottom of page 657. Okay. This is that volume of the parallelepiped. The U dot, the cross product of V and W, they wrote down and did what the cross product was there. And that turns out being the determinant of the U vector, V vector, and W vector. Okay. So that's just there. I can't think of what else to do with it. Now let's move to theorem 3. Yeah, and this then summarizes that. Sorry. Okay. Okay, area and volume via cross products and determinants. Let U, V, and W be non-zero vectors in R3. Then the parallelogram P spanned by U and V, in other words, wherever U and V is, they form a parallelogram. The area of that parallelogram is the magnitude of V cross W. Okay? See, it doesn't matter which order because magnitudes would be positive, so you can do W cross V because it's exactly the anti-commutative. Okay. The parallelepiped P, capital P, now this, they draw this as just a vector rather than a scalar, which is a little bizarre kind of, spanned by U, V, and W, U being some other vector, not collinear with either V or W, okay, has a volume now, U dotted with V and W, V and W being sort of like the base, this dot product of that being the height, and this you get from the determinant of the U vector, V vector, W vector, 3 by 3, and find this determinant, and that gives you the volume for V. Okay? All right. I think this is an example. Let's blow it up to begin with. And then we'll come back. Okay. Compute the area A of the parallelogram listed in this figure 13. It's figure 10 on the slide, but figure 13. Let me make sure that's no. Oh, I'm sorry. This is example 6. Sorry about that. Example 6. Let V be 1, 4, 5, just as shown here. Okay. And W be -2, -1, 2, which is shown there. Okay. Now again, I like to sort of visualize this. This is coming out 1 on the X component, 4 on the Y component, and then up 5 on the Z component. So that looks about right. Okay. Remembering that this plane is falling off here, so it doesn't look like it's 5 here until you realize that it is. W, on the other hand, is -2 on the X coordinate, -1 on the Y coordinate, and then up 2 in Z. So that looks about right. I can buy that. Okay? So there are our, this is figure 11 in the text, figure 10 on the slide. So slides got behind one. Calculate A. Okay? The area of the parallelogram spanned by V and W. So basically that parallelogram there. What is that area? Can anyone tell me? It is the magnitude of what? Earth to class, come in please. Okay. Magnitude of V cross W. Okay, that's the area. So first thing we've got to do is calculate what V cross W is. And what is V cross W? That's not too hard to do. It's I, J, K, and if you like my way of doing it, I, J, and that would be 1, 4, 5, 1, 4, and negative 2, negative 1, 2, negative 2, negative 1. Okay, and do the cross product. That's 8 plus 5 is 13I. Minus 10 minus 2 is minus 12J. Minus 1 plus 8 is 7 plus 7K. Okay. That's that. What's the magnitude of that? Square root of. Did I do it wrong?
Is it 13, right?
Okay, this is 8, I think, right? 8 plus 5.
That's 13.
13. Did I write it down wrong? What's that? Okay. Then the J component is minus 10, minus 2 would be minus 12, and the K component is minus 1, plus 8, plus 7. Is that right? All right. What's that? Okay. Now, well, I wanted fries with that. Okay. What would be the magnitude then? 13 squared, which is, I think, 169, plus 144, plus 49. Notice when you're doing magnitudes, you're squaring, they're all positive. Okay, so that's 313 plus 49, that's 362, and I don't think that's a perfect square, so that's the area of that parallelogram. What's that? Is that a perfect square? Look, oh no, it's approximately 19. Okay. Someone punch it on the calculator, see how close. Okay, wow, that is pretty close. About 19 square units, whatever they were. So that's the A part. This B part is find the, I'm pretty sure it's the volume of that parallelepiped. So what is the V? Okay, that's the V part. Okay, remember what that is. It's the, it's U, it's the absolute value of U dotted with V cross W. Right? We've already figured out what V cross W is. There it is right there. Our U vector, did they give us a U vector? Okay. Oh, I see. Okay, I see. It's right there. I was thinking it was off, but there it is. I see it. That's just 6K. So the U vector is 6K. Okay? So we're going to dot 6K with this one. That turns out pretty easy, doesn't it? 0, 0, 6. Okay? I'll do the 0, 0 part. Okay? You do the 6, and that gives us 42 cubic units of whatever it is. Okay? And that's it exactly. Okay. And you didn't have to do the determinant either. Okay? All you have to do is dot them, which is easier than doing a determinant.
We just did 6K times the 13.9 minus 12J plus 7K.
Yeah. And it's a dot product. So it's the 0 dot this, 0 dot that, 6 dot that, 6 dot that. Because it's a dot product. So if they hadn't already calculated this and just gave you V, W, and U, then to do the determinant, put a U in the top row and V cross W, V, W in the next two rows, that would have given you the same thing. Because U, top row, only had the K component. So forget about the X, the first two, just do that last one, and you would have gotten exactly this. Okay, good deal. Okay, that was example 6. Okay. Now, I'm trying to see what this next slide is. And I'm having trouble following what this is. This has nothing to do with what we just did. We compute the area A of a parallelogram spanned by vectors V, V1, V2, and W. Okay. By regarding V and W as vectors in R3 with 0 components in the Z direction, thus we write V as, okay, okay. Okay. I think I understand what they're saying here. If you have two vectors in the plane, XY plane, no Z components at all, and just in XY plane, we would say V is equal to AB and W is equal to CD. Okay? AX, V in the Y direction, C in the X direction, D in the Y direction. Okay? D, C in the X direction, and D in the Y direction. Okay. Okay. Now, if you're talking about the area of this thing, by what we just did, we crossed the two of those. But we cross them as a three-dimensional system, which would been you just have to add a 0 for your Z component there, knowing that the only thing that's perpendicular to the XY plane is going to be in the Z direction. So when you do the cross product here, the I component is going to be, picture this, 0, okay? Because you write this above that, and when you cross the I part, you get V0 minus D0, that's 0 minus 0, okay? Then do the I component, and if you picture A and C being moved out here, A, C, and cross those two, you still get 0, okay? But then when you do the K component, basically you can just consider these two, A, D minus BC, okay? That's going to be the area here. Well, that's going to be the magnitude of your V cross W, so that's why they put AK. At first, I was thinking they were throwing in a parameter A. It really is, it's the area A. That's all they're saying. It's, to me, it's sort of a strange way of saying it, but it makes sense when you think about it. And they show all that there. On the slide, it's A and B, C and D. In the book, it's V1, V2, and W1, W2. I'm not really sure why they changed that. Okay. So let's do, oh, well, okay. This leads to this conclusion, which is pretty much exactly what we did before. If you have two vectors in the xy plane, strictly in the xy plane, R2, okay, give them 0 components in Z, and then the area of that parallelogram that it forms is the determinant of that's the value of the determinant. If it comes out negative, you just do positive value of V and W written that way. But of course, with IJK, 0, 0 under the Ks. And that turns out being just the determinant of AD minus BC, which is exactly what we did before on the slide. I think in your book, let's see what your book calls it. It calls it V1, V2, W1, W2. That determinant. Same thing, it's just using different things. All right. Then I think we're ready for example, this example. Okay. Compute the area A of the parallelogram shown in this figure. Okay. Now notice this is XY space. This is a plane. This isn't three-dimensional. It's just the plane. Okay? And your W, the V vector is 1 unit on X and 4 units on Y. And the W vector is 3 units on X, 2 units on Y. So these two vectors, okay? What is the area of that parallelogram? Okay? Well, they just told you. Okay? Does it matter which order you do the cross? Usually you say you have to talk. Well, guess what? You're taking the magnitude of the answer, so it doesn't matter. So whichever way you want to do. The cross product would be the determinant of this. That would be 2 minus 12. That would be minus 10. Absolute value would be 10. So this would be 10 square units, whatever that happens to be. Okay. Yeah, 10. If you had crossed them the other way, you would have gotten 10 right off the bat. Is it near time? 3 more minutes. Okay, let's see what we can do in 3 minutes. They have some proofs here of cross products, and let's see what they show here. I don't know if this is helpful to you or not. Okay. Now, this is a rather strange one. What are they doing with this one? These are the properties listed in Theorem 1, way back, page 655, early on what we were doing, those 3 properties there. And here's how they go about proving those. Rather than having a third vector that's going up, you have the V cross W, which is in a plane somewhere, and dotting that with itself, with one of those vectors. Okay? Well, what if this better come out with B? Seems like to me it's got to be 0 because the cross product here has to be perpendicular, perpendicular to V and perpendicular to W. And when you dot this with something that's perpendicular to it, you ought to come up with a 0, okay? And what I can't figure now, if this is V, they're calling it A1, B1, and C1, but this V looks like to me, yeah, that's right. A1, B1, and C. Yeah, okay, they got it right. And then W is B2C. Yeah, okay. So yeah. Now, it seems like this is going around their elbow to get to the ear, okay? If that doesn't come up being 0, there's something really seriously wrong with this. And let's see what they do with that. We probably used our 3 minutes.
1 minute.
1 minute left, okay. Let's jump to this one next. This is a pretty important on its own right, and it's a you do use this a lot, but why it's showing up here, I'm not really certain why they're doing that. I don't think we can do it in a minute. What I'm going to say, this is just proving those other 3 things, and I'll let you read this. I'm not sure there's anything that we're going to be doing now that we really need this for it. They don't have any more examples with it, so I'll just do it as a slideshow. This is a fact, okay? The magnitude of a cross product of 2 vectors is equal to the magnitude of the first times the magnitude of the second minus the dot product squared. Okay, I'm sorry, magnitude squared, okay? If you think about this law of cosines, okay? Now, there's nothing that tells you this ought to be anything to do with law of cosines, but if you remember, it was a squared, b squared minus ab cosine the angle in between. That would be, basically, this is almost the same thing you got here, okay? Almost, and if you fiddle around with that much, you'll see that they are related, okay? And I guess we're out of time, so really the rest of these are just view and talk about, and not much talk about. So we'll just finish this real quickly next time, and then let me give you homework exercises in this. I think you can do 1 or 3 or both, 5 or 7 or both, 9 or 11 or both, 13 or 15 or both, 17, any of the odds 17 to 21, 23, I think I gave you some of these before, 25, any of the odds 27 through, wow, they have a whole passel of these, 27 through, let's say 47. And we'll hold off. No, I think you can do 49 or 51. Possibly 55. I'll say any of the other odds through 61. We'll hold off there and pick up there next time. Okay, almost the rest of the section. Just a little bit left to go in that, not much. By the way, we're going to finish cross product, that's this section, and then we'll talk a little bit about planes in 3 space, that's very short, and then we'll get into our quadratic surfaces. Then we'll have a test on chapter 12. Now, wait, did I give you anything on 11? Huh? No, okay, so the test will cover the first 2 sections of 11, I believe it was, and then most of this. I'll be light on some of these sections, but once we finish chapter 12, we'll have a test on 11 and 12 together, mostly on 12. Good deal. Let me end the recording.